Welcome to Unit 5, Lesson 4, Concavity and the Second Derivative Test. In this lesson, our standards will be functions-4.a.4. The graph of a function is concave up or down on an open interval if the function's derivative is increasing or decreasing on that interval. A.5, the second derivative of a function provides information about the function and its graph, including intervals of upward or downward concavity. A.6, the second derivative of a function may be used to locate points of inflection for the graph of the original function. A.7, the second derivative of a function may determine whether a critical point is the location of a relative or local maximum or minimum. And A.8, when a continuous function has only one critical point on an interval on its domain, and the critical point corresponds to a relative or local extremum of the function on the interval, then that critical point also corresponds to the absolute or global extremum of the function on the interval. The instructional objective for this lesson is that students will be able to interpret the behavior of derivatives in order to justify conclusions about the behavior of a function. And our inquiry question is, how can a function's derivative be used to understand some behaviors of the function? This lesson focuses on topics 5.6 and 5.7 from the 2019 Course and Exam Description for AP Calculus AB. Determining concavity of functions over their domains and using the second derivative test to determine extrema. In this lesson, we will use second derivative test to find points of inflection and concavity of a function. We will also use the second derivative test for extrema to find relative max and relative min values. Concavity and the second derivative test. In our last lesson, we found intervals on which a function was increasing or decreasing and discovered how the first derivative describes the direction of a function, how the y values are changing. In this lesson, we will see that the derivative of f prime of x, that is, the second derivative, will describe the concavity of the original function. Concavity tells us the direction of the curve, or how it bends. Just like direction, concavity of a curve can change too. The points of change are called inflection points. In this first exploration of concavity, we're told to draw small tangent lines at points along the curves below. And then we're asked, what do you notice about the slopes of the tangent lines, or the derivatives, as you move from left to right at these points? So let's draw some tangent lines. So in part A, the tangent lines lie below the graph of f. So let's take a minute and think about the slopes of these tangent lines. I'm going from negative to positive, and then it gets steeper and steeper. In this case, we can see that f prime is increasing. In part B, we have tangent lines lying above the graph of f. In this example, we can see that we're going from a positive slope, or f prime, to a negative value, and the slopes are getting steeper and steeper in the negative direction. So this means that f prime is decreasing. Now you'll also notice that in this case our function f of x is concave up, and this function is concave down. So this brings us to our definition of concavity. If we let f be a differentiable function on an open interval I, the graph of f is concave upward on I if f prime is increasing on the interval I. And it's concave downward on I if f prime is decreasing on the interval I. So if we're talking about a function's increasing or decreasing behavior, we're talking about a positive or negative slope or first derivative. In this case, we're talking about whether f prime is increasing or decreasing. So it makes sense for us to take the first derivative of the first derivative. And if we do that, we get the second derivative. Now all we need to do is look at the sign of the second derivative, and we will know if the first derivative is increasing and if the original function is concave up. If the second derivative is negative, that means the first derivative is decreasing and the original function is concave down. So this is our test for concavity. If f double prime of x is positive or greater than 0, then the graph of f is concave up. If f double prime of x is less than 0, negative, the graph of f is concave down. In example 1, we're given f of x equals 1/3 x cubed minus x and told determine the open intervals on which the graph is concave upward or downward. We'll begin by taking the first derivative. So f prime of x is equal to 3 times 1/3, which is 1 times x squared, minus, and the derivative of x is 1. Second derivative is equal to 2x. Now, I want you to think back to concavity and our test for concavity. Remember, the test for concavity says where f double prime is positive, it's concave up. Where it's negative, it's concave down. Now, I want you to think back to where we said, just like direction, concavity of a curve can change too. It can change from upward to downward or vice versa. And so the point where that change happens is called an inflection point. Okay, this is important. So if positive f double prime means concave up and negative f double prime means concave down, what is f double prime equal to where the concave is, or where the concavity is changing? Well, if we're going from positives to negatives and from negatives to positives, that means that at that transition point, f double prime would have to be equal to 0. So what we'll do is set 2x equal to 0, and we'll solve, and we get x equals 0. Now, here's my question. Does it have to be a point of inflection? Well, okay, here's the deal. Suppose I were to graph f prime. And I know this is a quadratic, but let's just assume it was a cubic, for instance. I mean, I might have an f prime that looks, you know, something kind of like this, only well, here's one that's a little bit nicer. So I've got this point here, this point here. So if this is a graph of f prime, the concavity of f prime is changing, but maybe not necessarily the concavity of our original function f, because look, my f double prime is f prime is increasing on both sides of this point. That means that f double prime, the slope of f prime, is going to be positive on the left side of that point x equals 0, and it's positive on the right side also. So just because it's equal to 0 doesn't mean that it is a point of inflection. What it means is that it could be. And so what we'll have to do is we will have to look and see if f double prime does in fact change directions on either side of 0. And if it does, then this is a point of inflection. And if it doesn't, then it's not a point of inflection. So let's do this. Let's put x equals 0 on our sign chart for f double prime. And I want to know, what is the sign of f double prime? If we plug in negative numbers to the left of 0, then we get 2 times those numbers, they're negative. So this is going to be negative, 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 negative. If we plug in positive numbers greater than 0, we get a positive f double prime. Now, where it's negative, f is going to be concave down. Where it's positive, f is going to be concave up. So let's write f of x is concave up on the open interval from 0 to infinity, cos f double prime of x greater than 0. F of x is concave down on the open interval from negative infinity to 0, cos f double prime of x is less than 0. Now, remember what we said? In order to verify whether we have a point of inflection here, we have to check and see if the signs are different on either side. Because if they're both positive or both negative, and we have a graph that is just turning, this is a turning point for that first derivative, it's not going to be a point of inflection for the original function. It might be a point of inflection for the first derivative, but that's not what we're asking. All we have to do is look at our sign chart, and here we see that we do in fact have different signs on either side of 0, and that is enough for us to conclude this, yes, this is a point of inflection. So we can write at x equals 0, f of x has a point of inflection since f double prime 0 equals 0. So that's the first criterion, and here it comes. F double prime of x changes from negative to positive here. Alright, so looking for open intervals with concave up, concave down, all we have to do, take the second derivative of the function, set it equal to 0, we have a candidate for point of inflection, set up a sign chart for f double prime, plug numbers in on either side of our possible point of inflection. If the signs are different, that means this is a point of inflection, and so where it's negative, it's concave down, where it's positive, it's concave up. If the sign doesn't change, then it could be maybe concave up on both sides, or it could be concave down on both sides, and in this case we would not have a point of inflection. In example 2, we want to look at the relationship between graphs and derivatives, and so the concavity f double prime of x and direction f prime of x of the function f of x is related to the slope of the derivative. So let's take a look at this. So here we have f of x equals 1/3 x cubed minus x, and if we graph this, we get something akin to this. So we've got a function that looks kind of like this, and let's think about this a minute. So notice that the slope is going to be tangent to the curve at these points and equal to 0. So that means these are our critical values right here. So the critical values occur where the slope of the function is equal to 0. In other words, where f prime equals 0. And here's our f prime. If we set this equal to 0, we get plus or minus 1. So this is 1, and this is negative 1. And we can see here that f prime of negative 1 is equal to 0. F prime of 1 is equal to 0. Now the other thing we notice is that this is our point of inflection right here, isn't it? This is the point where the concavity changes from concave down to concave up. And this is f double prime of x equals 0. If we do a sign chart for f prime, let's put our critical values on here. Negative 1, positive 1. And let's think about what f is doing. So when f is less than negative 1, my slope is positive. When I am between negative 1 and positive 1, my slope is negative. And when I am greater than 1, my slope is positive again. Now for f, that means that my function is increasing, decreasing, and increasing. Now let's take a look at the graph of f prime of x. So here's our graph of our quadratic, and this is going to be negative 1, and this will be 1, and this is also -1. Now, where was our point of inflection? Well, that's where the slope of f prime is equal to 0, and that is f double prime. So f double prime of 0 is equal to 0. So that's our point of inflection. And you can see it is a point of inflection because f prime is negative. I'm sorry, it has a negative slope. F double prime is negative on the left. F double prime is positive on the right. The function is decreasing to the left of 0. It's increasing to the right of 0. Point of inflection right here where f double prime changes from positive to negative. That's f prime of -1. It's equal to 0. And that corresponds to our maximum value. And this point, f prime of 1 equals 0. Look at our function f prime. It's negative to the left and it goes positive. So if we're going from negative to positive, that's going to be a minimum value. And that's exactly what happens. Now if we do a sign chart for f double prime, we have 0. F prime is decreasing to the left of 0, so that means that f double prime is negative. F prime is increasing to the right of 0, so f double prime is positive. So f is concave down, and here f is concave up. Now let's layer one more piece of information on here, f prime. So when f prime is less than 0, when we're less than 0, f prime is actually going to be decreasing, and to the right of 0, f prime is increasing. And here we have a picture of the relationship between all three of these, f prime, and f double prime. And I'll give you a way to remember this, that this is actually kind of my go-to mnemonic or memory device for these types of problems. What I'll do is I write down, I'm going to do this in a bright color. I write down f prime, and f double prime. And I write plus, minus, up, down, concave up, concave down. You can make a little song out of it, but plus, minus, up, down, concave up, concave down. So notice I skipped 2 and started again. So now I'm going to skip 2 again, and I get plus, minus, up, down, concave up, concave down. So it's plus, minus, up, down, concave up, concave down. Plus, minus, up, down, concave up, concave down. So what you've got here when you're done is a chart that outlines these relationships pretty nicely. You can see that when f double prime is positive, f is concave up. When f prime is decreasing, f is concave down. So if they give you any one of these pieces of information about f prime, or f double prime, you can answer a question about any one of the remaining two. If they tell you that f is increasing and they say, what is f prime doing? It's positive. If they say, well, f prime is concave up, what's f double prime? You can say, well, it's increasing. So you can answer now all of these types of questions that can be asked just by memorizing this little chart, and you can re-represent these relationships. So let's define our point of inflection formally. So let f be a function that is continuous on an open interval, and let c be a point on the interval. If the graph of f has a tangent line at this point, c, f of c, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward at this point. So in words, that's what a point of inflection is. Now, a couple of characteristics. If c, f of c is a point of inflection of the graph of f, then either f double prime of c is equal to 0 or f double prime of c is undefined. Now, I want to point out the way this if-then statement is written. It says if this is a point of inflection, then your f is going to be 0 or undefined. But just because f double prime is 0 or undefined, that doesn't necessarily mean that Cf of C is a point of inflection. Remember, you have to check and see if you have a sign change on either side of this value C. So here we have a function f of x, and we can see that the concavity changes from concave up to concave down. Now if we let the point where this transition occur be called P, then you can see the slope of the tangent line passing through P is positive. So that means that f prime of P is greater than 0. But the problem is that f prime of x is a constant at x equals P. And so therefore f double prime of P is going to be equal to 0. Now in our next graph of f of x, we have a horizontal tangent line at x equals P. So in this case, that means that f prime of P is equal to 0. And the derivative of 0 is also 0. And once again, our point P divides the graph into two regions where it is concave up and concave down. So in both of these cases, we have a situation where our point of inflection divides our graph f from two regions that are concave up and concave down, or vice versa. And in both cases, the second derivative is equal to 0. Let's take a look at the third example. So in the third example, we have our function f of x, and we can see that our point P again divides the function in such a way that to the left of P, or for x values less than P, our function is going to be concave up. And for x values greater than P, it's going to be concave down. And so P then should be a point of inflection because the first derivative of P is undefined. And so therefore, the second derivative of P will also be undefined. So if you have a point where the concavity of f changes at a point of inflection, then it's going to occur where the second derivative is equal to 0 or does not exist. And that's going to be true in every case where the concavity changes. And so that's the second derivative rule in a nutshell. So let's explore the possibility that a graph could change concavity at a discontinuity, say a vertical tangent line, or where f doesn't exist, such as a cusp. In the case of a vertical tangent line, where the x value is not in the domain of the function, then the value x equals P will not be a point of inflection. So let's look at a few examples of this. So in our first example, we have the concavity changing from concave down to concave up. And that's happening again at this point x equals P. And so we can say that f double prime of P is equal to 0. Now likewise, here on this part of the graph, we are concave up. And over here we are concave down. And so once again, here at point P, we have a situation where f double prime of P does not exist. And so these are both examples of where P is an inflection point for the graph. Let's look at a couple of examples where P is not an inflection point for the graph. So in this example at the top, again, f double prime of P does not exist. However, the graph goes from concave up to concave up. So there's not going to be an inflection point at P, and because we have a cusp. Now if we look at this graph, we can see that P is actually not in the domain of f. And so P doesn't exist as a point, and we have x equals P is a vertical asymptote. So here are some important ideas. First, we will use a second derivative sign chart, much like we did with the first derivative test, to determine intervals of concavity as well as actual inflection points. The possible points of inflection can be called critical values of f prime of x. Remember also that concavity can change at a discontinuity, such as a vertical asymptote, but it won't be an actual inflection point. In order to classify an x value as an inflection point of a function f of x, the x value has to be in the domain of f. In example 3, we're told to determine any points of inflection and discuss concavity of the graph f equals x to the fourth minus 4x cubed. So this is a polynomial, so it's everywhere continuous and everywhere differentiable. We'll begin by finding the first derivative. So f prime of x is, via the power rule, 4x cubed minus 12x squared. And we can factor a 4x squared out of both terms, and that leaves x minus 3 in parentheses. And to find the critical values of f, we set this equal to 0, and we find that x equals 0 or x equals 3. Now let's go ahead and find the second derivative. So the second derivative is going to be the derivative of f prime. So that'll be, again by the power rule, 12 x squared minus 24x. And if we factor a 12x out, that's going to leave x minus 2 in parentheses. And we can set that equal to 0. And now we have our critical values for f prime, which again is going to be x equals 0, and this time x equals 2. Okay, so let's make a number line. And the critical numbers here are going to be the critical numbers for f prime. So those will be the ones that we got from the second derivative. So 0 and 2 are those critical values. So the next thing that we'll do is pick some test values. So -1 would be to the left of 0. +1 is between 0 and 2, and +3 is to the right of 2. And so what we will do is plug these test values or test numbers into the second derivative. And so if we do that, we're just looking for what's the sign of f double prime. So -1 squared is +1 times 12 is 12, and -1 times -24 is +24. So a positive number plus a positive number is a positive number. And so on this first interval, f double prime is positive. Now let's look at what happens on the second interval. So if we plug 1 in, we have 1 squared is 1 times 12 minus 1 times 24. That's going to give us a negative number. So we have negative values on this center interval. And then on the outside interval, we've got 3 times x squared is 9 times 12 is 108 minus 3 times 24. And so that'll be 72. So we end up with a positive value again. Now, what does this mean for concavity? Well, it means that since the second derivative is positive, our graph is going to be concave up in both of these regions and concave down here. So here's our conclusion. 1. We have points of inflection occurring at f of 0 equals, and if we plug 0 into f, if we plug 0 into f, we get 0. And f of 2 equals, and if we plug 2 in, I think we get -16. And you could write these as ordered pairs, 0, 0, 2, -16. But that's where the ordered pairs come from. Substitution into the original function. So part 2, we know that f of x is concave down on the interval 0 to 2, and the reason for that is that f double prime of x is negative. And then finally, f of x is concave up on negative infinity to 0 union 2 to infinity, and the reason for that is f double prime of x is positive. Example 4. Find the inflection points in the open intervals of concavity. Justify. Given g of x equals 1/2 x plus sine x on the closed interval from 0 to 2 pi. So we'll begin by finding the first derivative. G prime of x is equal to 1/2 plus cosine x. And then if we go ahead and take the second derivative, g double prime x is equal to, and the derivative of 1/2 is 0, and the derivative of cosine is negative sine x. Now to find our critical values, we set this equal to 0, and that gives us sine x equals 0. And so x is going to be an element of the set containing, for this closed interval, 0, pi, and 2 pi, and we get those values directly off the unit circle. That's where sine x is equal to 0. Okay, but let's think about this. Now 0 and 2 pi are both endpoints, and so there's no way that either of those could be points of inflection. And so that means, as far as we're concerned, we're just interested in x equals pi. Now let's go ahead and see if we can make a sign chart. So here are the endpoints, 0 and 2 pi. And right in the middle we have pi. And so what we're going to do is pick a test value on each of these intervals. And so halfway between 0 and pi is pi over 2. And halfway between pi and 2 pi is 3 pi over 2. Now I need to find out what g double prime of pi over 2. So g double prime of pi over 2 is going to be negative sine pi over 2. Sine pi over 2 is 1, so negative sine pi over 2 would be negative 1. So this interval contains negative values for g double prime. These are our test values, and these are our critical. All right, what about g double prime of 3 pi over 2? Well, okay, sine of 3 pi over 2 is negative 1, so negative sine would be negative 1, which is positive 1, and so this interval contains positive. So let's find out what this inflection point is. So we go back to our original function, g of x, and we substitute in pi, and we find the corresponding y value. So 1/2 pi plus sine of pi, so that goes to 0, and we're left with pi over 2. So our point of inflection is going to be pi, comma, pi over 2. So we can say point of inflection is pi, comma, pi over 2, cos double changes signs from negative to positive at x equals pi. So next we can say that g of x is concave down on 0 to pi, since g double prime is negative. And then finally g of x is concave up on pi to 2 pi, since g double prime of x is positive. And so this is our solution with justification. In example 5, we're told to use a calculator to find how many times the graph of y equals x squared minus 3 plus sine 2x minus 1 changes concavity on the interval from 0 to 2 pi. So we'll begin by taking a couple of derivatives. So y prime is going to be 2x, and the derivative of negative 3 is 0, plus, and the derivative of sine is cosine 2x minus 1, and then via the chain rule, the derivative of the inside is 2, so 2 comes out. So now let's take the derivative again to get our second derivative. And the derivative of 2x is 2. The derivative of cosine is negative sine. So negative, and then sine 2x minus 1. The derivative of the inside again is going to be 2, but remember we already had a 2 out front, and so we'll multiply those and have 4. And so 2 minus 4 sine 2x minus 1 is my second derivative. Now if we set this equal to 0, we have a trigonometric equation to solve. And so if we bring 4 sine 2x minus 1 over to the right side, we have 2 equals 4 sine 2x minus 1. And then if we divide both sides by 4, we have sine 2x minus 1 equals 2 divided by 4, which is 1/2. And so now I have to think about the unit circle. Okay, so where on the unit circle is sine theta equal to 1/2? Because that's what I want. Sine theta equals 1/2. Well, okay, that's going to happen here. And that's going to be square root of 3 over 2 comma 1/2. And this angle theta is pi over 6. And it's going to happen again right over here at the same place, but reflected about the y-axis. And that is going to be negative square root of 3 over 2 1/2. But more importantly, the angle here is going to be theta equals 5 pi over 6. So if you just count by pi over 6, you'll get there. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. All right, so that means that theta is equal to pi over 6, or theta is 5 pi over 6. So in this case, sine theta is actually 2x minus 1. So what I have to do is take 2x minus 1 and set that equal to pi over 6. Okay, but here's the deal. I can go around multiple times. And the question is, how many times can I go around before I hit the 2 pi? Using the original function here, not just sine. So I'm going to have to do this. I'm going to have to consider that I can go to pi over 6, but I could also go around one full revolution and come right back to that same point. And I can do this an integer number of times. And so for that reason, I'm going to add to pi over 6 2 pi n. And that's going to give me a general solution to this equation. And then we'll do the exact same thing for the other value. 2x minus 1 equals 5 pi over 6 plus 2 pi n. Now this means that 2x is going to be equal to 2 pi n plus pi over 6 plus 1. 2x equals 2 pi over n. Sorry, 2 pi n plus 5 pi over 6 plus 1. All we did was just add 1 to both sides. Now I'm going to divide through by 2. And so that'll give us x equals, and 2 pi n divided by 2 is pi n plus pi over 6 divided by 2 is pi over 12 plus 1/2. Over here we have x equals 2 pi n divided by 2 is pi n plus 5 pi over 6 divided by 2 is 5 pi over 12 plus 1/2. And so x equals 12 pi n plus pi plus 6, all divided by 12, getting a common denominator. X equals 12 pi n plus 5 pi plus 6 divided by 12. And this is the part where you get your calculator out. We did all of this work, and now it's time to use the calculator, because n is equal to 0, 1, 2, 3, so on and so forth. And so what we'll do is we'll put each of these equations into our calculator for y1 and y2, and we'll just repeatedly substitute these values. And so what we get is x equals, some of these will be duplicated by each of these formulas, but we end up getting 0 to 3 decimal places, 0.76, I'll just round it to 4, 18, comma, x equals 1.809, comma, x equals 3.9033, comma, x equals 4.9505, comma, and the very next one is x equals 7.0449. Okay, stop. So our angle, which is x, is on the closed interval from 0 to 2 pi, but remember that 2 pi is approximately 6.28. So this is the very first value that cannot be a solution for x. And so what we have is a set of 4 possible solutions, and you can write that as a solution set, but I'll just circle it for now. Now in example 6, they tell us using a calculator find the values of f of x equals e to the x times x squared, at which the graph of f changes concavity. So to do this, we'll use our graphing calculator. So the first thing that we'll do on our graphing calculator is input the original function, and so it's going to be e to the x, so that's second natural log x right arrow times x squared, so x and then x squared, enter. And it might be good just to graph this and kind of see what it looks like. It's kind of hard to tell what's going on as we get close to the x-axis, so let's get tight on the x-axis, and the way we'll do that is we'll go to Window Settings, and I'm going to leave the x settings alone, but I'm going to change y-min to -0.5 and y-max to +0.5, and then graph. And we get a lot better picture of what's going on. Here we can see a region of concavity. It's concave up, and then here we have concave down, and then concave up again. So presumably we've got 2 points of inflection. Let's see if we can find them in case we're asked to do that. So what we'll have to do to find points of inflection is determine where the second derivative is equal to 0. Let's go back to y equals. And so in y2, we're going to let this be the first derivative of our function. So we go to Math, 8, and then x, and then y1. Sorry, that should be y1, this should be x. There we are. Enter. And so now to find the second derivative, I'll need to take the derivative of y2, the derivative of the derivative. So we'll go to Math. Unfortunately, you can't do a second derivative in one function on the TI. You just take one derivative and you can repeat that process. So we'll take the derivative now of y2 with respect to x. Enter, and let's graph those. So there is y1. I'm sorry, there is y2 in red and y3 is in black. So remember, y3 is the second derivative. Now I would expect there to be a point of inflection somewhere around here, because that's where the concavity changes from concave up to concave down. And in fact, our second derivative crosses the x-axis right there. And then we have another point of inflection going from concave down to concave up, and that's going to be where our y3 second derivative crosses the x-axis here. So if you want, you could zoom in a little bit more. Maybe let's go from -10 to 2. And we're just going to use our solver to find what the roots are for y3, our second derivative. So to do that, we'll go to second trace or second calc, and then 0 to find the zeros. Now it starts out on our very first function y1, so I'll hit the down arrow and it drops us onto y2, and then one more time drops us onto y3. That's the second derivative. And you know what? It looks like I am to the left of that first intersection, so I'm just going to press enter. And then it looks like 1, 2, 3. -3 should be to the right of that intersection, so I'll just type -3. And that saves you from scrolling with your arrow keys. And we'll just press enter. And we see that our first intersection is -3.414214. Let's find this one over here. So that's going to be between -1 and 0. So we'll do second trace 0. Left up, we need to go back to y3. So we're on the second derivative, and we're going to go from -1 to 0. And -0.585787. So that gives us our x values corresponding to points of inflection. So they wanted us to find values at which the graph of f changes concavity, so we can write that there are 2 points of inflection, and we'll report those to 4 decimal places. So x is approximately -0.5857, and x is approximately -3.4142. And if you want, you can sketch a representation of the graph and just indicate those points of inflection. So we could say x1, x2, so this will be x1 and this will be x2. Alright, so topic 5.7 is using the second derivative test to determine extrema, and here's how we'll do that. So the second derivative is the first derivative of f prime. So the same relationships that exist between f and f prime also exist between f prime and f double prime. So we can use the second derivative test as an alternate method for locating relative extrema. If x equals c is a critical number of f of x, then f prime of c equals 0, or f prime of c does not exist. This makes x equals c a possible maximum or minimum value of the function f. So if f double prime of x is positive, that means that f prime of x must be increasing, because if the function is increasing, the slope is positive. But if f prime of x is increasing, that must mean that the original function. Likewise, if the second derivative is negative, that means that the first derivative is decreasing. And if it's decreasing, f of x must be down. Now, if f double prime of x is neither positive nor negative, that means it's a possible point of inflection for the original function. Remember that it could be that if the concavity is the same on either side of that point where you've taken the second derivative, it won't be a point of inflection. So that's the reason why we have to go and check the concavity on either side by looking at the sign of f prime on either side. Now what that means for f prime of x is that this will be a possible relative max or min at this point. In example 7, we're told to use the second derivative test to find the relative extrema of each function and then justify. So f of x equals x to the fourth minus 8x cubed minus 5. And we'll begin by taking the first derivative. So f prime of x is 4x cubed minus 3 times 8 is 24x squared, and the derivative of -5 is 0. So to find critical values, we'll set 4x squared, let's factor out a 4x squared. 4x squared times x minus 6 equals 0. And we get x equals 0 and x equals 6. And these are going to be our critical values. Now we'll take the second derivative. So f double prime x is equal to 3 times 4 is 12x squared minus 2 times 24 is 48x. And we're going to see what is the sign of the second derivative at the critical values. So f double prime of 0 is equal to 12 times 0 squared minus 48 times 0 is equal to 0. And furthermore, f double prime of 6 is going to be 12 times 6 squared minus 48 times 6. And that's actually going to be equal to 144. All right, now let's do this. Let's find out what the corresponding y value is for the critical values. So our two critical values are 0 and 6. And f of 0 is -5. F of 6 is, substituting in and calculating it, we get -437. So 0, -5, 6, -437. And f double prime of 0 was 0. And f double prime of 6 was positive. So our conclusion is that a local minimum occurs at x equals 6 and is -437 because g double prime of 6 is greater than 0. So g is concave up. So the idea is if it's concave up on that interval, then that critical value doesn't correspond to a maximum, it corresponds to a minimum. And then number 2, we can draw no conclusion above x equals 0 since g double prime of 0 is equal to 0. In part B, we have f of x equals 1/2 x minus sine x on the closed interval from -2 pi to pi. Let's go ahead and take the first derivative so that we can find our critical values. So f prime of x is equal to 1/2 minus, and the derivative of sine is cosine x. And we'll go ahead and set that equal to 0 so we can find our critical values. And so that means that cosine x is equal to 1/2. Now, if you think about the unit circle, where does cosine x equal positive 1/2? Well, it happens at pi over 3, and it happens again at negative pi over 3, or 5 pi over 3. And those are the only two times that happens on the interval from 0 to 2 pi. Okay, but this is a little weird. Instead they gave us -2 pi to pi. So we're going to have to think about what that means. Now, if I start at 0 and I go in the negative direction, that means I go clockwise instead of counterclockwise. Counterclockwise is positive, clockwise is negative. So starting at 0, if I go clockwise, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. This is now my starting point. But I have to translate pi over 3. So pi over 3, this point here, the first time cosine is 1/2 on this interval is when negative 2 pi has pi over 3 added to it. So what we're doing is we're going to start at negative 2 pi, we're going to add pi over 3, and now we're at this point. What is this? Well, common denominator, negative 6 pi over 3 plus 1 pi over 3 gives us negative 5 pi over 3. So that's my first critical value. Now I go all the way around until I get here, okay, but I'm still in that negative 2 pi to 0 range. So let's do negative 2 pi, and let's add to negative 2 pi 5 pi over 3, and that's going to be negative 6 pi over 3 plus 5 pi over 3, and there's negative pi over 3. So this angle is now going to be, starting at negative 2 pi, it becomes negative pi over 3. And then I'll keep going because remember, pi is where I can end. So if I go around one more time, I pick up positive pi over 3. So I have three critical values. Critical values, we'll say x is an element of the set containing negative 5 pi over 3, comma, negative positive pi over 3. So with three critical values, we'll divide our table up into three different sections, and let's put those critical values in. Negative 5 pi over 3, negative pi over 3, and pi over 3. Now we have to find out what f of c is. In other words, the corresponding y values that go with each of these critical values. And to do that, we'll simply plug negative 5 pi over 3 in to f of x. So f of negative 5 pi over 3, and that's going to give us negative 5 pi over 3 times 1/2, which is negative 5 pi over 6, minus sine of negative 5 pi over 3, and that's going to be negative 5 pi over 6 minus, and the sine value is square root of 3 over 2. So at negative 5 pi over 3, negative 5 pi over 3, the sine value is positive square root of 3 over 2, but we're subtracting that, so minus square root of 3 over 2. Now let's do f of negative pi over 3. So negative pi over 3 times 1/2 is negative pi over 6 minus the sine of negative pi over 3. This is negative pi over 3. Sine is negative square root of 3 over 2. So minus a negative square root of 3 over 2. So that'll be negative pi over 6 plus square root of 3 over 2. And you can write square root of 3 over 2 minus pi over 6 if you want to. And then let's find the third one. F of pi over 3 is equal to 1/2 times pi over 3 is pi over 6 minus sine of pi over 3, and sine of pi over 3 is square root of 3 over 2. So we have pi over 6 minus square root of 3 over 2. Got to memorize that unit circle. So go back and review that if you need to. All right, next thing we're going to do is take the second derivative. So the first derivative was 1/2 minus cosine x. So the second derivative, f double prime x, is going to be equal to, the 1/2 goes away, cosine is negative sine. That's minus a negative sine x, which is positive sine x. So now we substitute each of these values respectively into f double prime. And we're just going to check and see what's the sign that we get. So if we plug negative 5 pi over 3 into sine, you can do this on your calculator, we get positive values. Now if it's not a calculator problem, use your unit circle. Negative 5 pi over 3 we said was corresponded to this pi over 3. So sine pi over 3 is positive square root of 3 over 2. So it's positive. Alright, so the next one was negative pi over 3. That's down here. That's going to be, the sine value there is negative square root of 3 over 2. So it's negative. And then we're back up to this one again. Positive pi over 3, sine of that is positive square root of 3 over 2. Alright. So let's draw some conclusions. Part 1. Local mins are negative 3.4x, negative 5, 3, and we'll say that's approximately, and approximately negative 0.342 pi over double prime of x is greater than 0, and so it's got to be a minimum value if it's concave up. All right, and then 2, local max value is approximately 0 equals negative pi over 3, since f double prime of x less than 0, f concave down. Example 8 says the graph of f prime, the derivative of a function f, is shown. On what open intervals is f, the original function, increasing? Justify. Okay, so here's the thing. If this is f prime, I just need to find where is f prime positive and f prime negative. So on the interval, well, let's make the statement. Let's say f increases where f prime of x positive. So where does that happen? So f prime is going to be positive. It's where the graph is above the x-axis, and so that happens. So this occurs on the interval from negative infinity to a, and it also occurs on the open interval between b and c, because that's where f, so we can also say union bc. In part b, it says at what values of x does f have a local maximum or minimum? Justify. So if we go back to our original function, we can create a sign chart that will help us out with this. But the first thing that I want to do is to reacquaint myself with the relationships between f, f prime, and f double prime. So what I'm going to do is go off to the side and I'm going to write f, f prime, and f double prime. So I'm going to write plus, minus, up, down, concave up, concave down. Plus, minus, up, down, concave up, concave down. Plus, minus, up, down, concave up, concave down. Alright, so with our memory device, we've got all the relationships that we need to interpret the relationships for any graph that we're given. Let's take a look again and see what we're being asked. So at what values of x does f have a local maximum or minimum? So notice that they've asked me about x, but they've given me a graph of f prime. So let's make a sign chart for f prime. Now remember that the critical values are the values of x for which f prime is equal to 0, and we can see from the graph that happens at a, b, and c. So we can put our critical values in, and once we have our critical values written in, now we can look at f prime and determine where is it positive, where is it negative. And we've already kind of dealt with that in part A, so we still have our graph labeled. But to the left of A, it's positive. And between B and C, it's also positive. Now between A and B, f prime is negative. It's below the x-axis. And to the right of C, it's also negative. Now, what does that mean for f? Well, so here's what I'll do. I'll go and I'll find, okay, when f prime is positive, that means that f is increasing. So I'm going to come down here next to f and I'm going to put increasing. And then where, we'll do it over here as well. And then where f is negative, we're going to put negative corresponds to decreasing. So I'll put decreasing. So now I can see that A has to be a maximum for f because it's increasing to the left and decreasing to the right. C has to be a maximum for f. It's increasing to the left, decreasing to the right. B has to be a minimum. Decreasing to the left, increasing to the right. So let's write that up. So we can say f has a local max at x equals a and at x equals c, because f prime of x changes sign from positive to negative at these values. And further, we can say f has a local minimum at x equals b because f prime of x changes sign from negative to positive. Part C says state the inflection points of f and justify. Well, if we go back to our graph, we can see that, remember, the inflection points will occur where the second derivative is equal to 0 or does not exist. And so what we're looking for on our graph of f prime is the slope of the graph of f prime. That's f double prime. And in particular, I'm looking for places where the slope is undefined or equal to 0. And there are no places where this is undefined because this is a continuous function that is everywhere differentiable. But at this point, -1, -3, we have a horizontal tangent line, or a slope of 0. And likewise, at point 3, 2, we likewise have a horizontal line. And so that means that the slope is equal to 0, and that's the slope for f prime, which means that's the derivative of f prime, which means that's f double prime. So f double prime equals 0 at each of these points, so therefore they must be inflection points. Let's make the argument. So we can say f has points of inflection at x equals -1 and at x equals 3 because f double prime of -1 equals 0 equals f double prime of 3. In part D, they ask on what intervals is the function f concave up or concave down. Now, thinking about concavity, remember that the concavity of the original function is broken up by points of inflection. And also remember, we're not looking at the original function f, we're looking at f prime. And so while f prime has its own concavity, that is not something that we want to even be thinking about in terms of the original function f. And that's a very common thing that can be confusing. And so what we have to do is look at this function and say, okay, well, you know what? Where are the points of inflection for the original function? And we just found those. They're located at x equals -1 and x equals 3. Now, here's what we're going to do. Remember that if the original function is concave up, okay, so if the original function is concave up, f prime is increasing and f double prime is positive. So let's do this. Let's make another sign chart for f double prime. And instead of putting a, b, and c, critical values for f, we're going to put critical values for f prime, places where f prime was equal to 0. So we're going to put f double prime on top, and we'll put f on the bottom. And I'm going to make points at -1, which was our first critical value for f prime, and 3, which was our second critical value, f prime. So notice that to the left of -1, f prime is decreasing. It's decreasing to the left of -1. So if I go over and I say, okay, what happens when f prime is decreasing? Well, that means that f double prime is negative, and it means that f is concave down. Now, between -1 and 3, we can see that f prime is increasing. The graph is increasing on that interval, and so that means that f double prime is positive. It has a positive slope, and it means that the graph is concave up for f. And then finally, from 3 to infinity, f prime is decreasing. That means that f double prime is negative, and it means that the original graph f must have been concave down. So for part D, let's go ahead and write f is concave up on -1, 3, since f double prime of x is positive and f is concave down on negative infinity to -1. So negative infinity to -1 and 3 to positive infinity, since f double prime of x is negative. Alright, now in part E, they tell us to assume that f of 0 is equal to 0. So we'll put a point at the origin. And then they say, can you sketch a graph of f of x? Okay, well, here's what we're going to do. We're going to begin by laying out the critical values for f. So that was A, it was B, and it was C. Now I'm also going to put in the critical values for f prime, which were our points of inflection. So we had one located at -1 and another located at 3. Now we had a maximum located at A. We had a minimum located at B. Another maximum at C. We had a point of inflection located at 3 and a point of inflection located at -1. And so I'm just going to sketch a curve through all of these points. Now, the nice thing about AP readers is what you lack in drawing ability, you can make up for with labeling. So we're going to put A, comma, max, and down here we're going to put B, comma, min, 0, 0. This is C, comma, max. This is point of inflection. And this is point of inflection. And I think that's good. I think that we have captured the essence of the graph. In example 9, we're told in the table at right, selected values for g of x, g prime of x, and g double prime of x are shown. The function y equals g of x is a twice differentiable function, and it goes without saying, but they said it anyway, continuous on -4 is less than or equal to x is less than or equal to 5. If it's differentiable on the interval, it has to be continuous on the interval, but they gave us both of those. Part A says, explain why there must be a value x equals c on the open interval from -4 to 5. So here's -4, the x value, here's 5, the x value, such that g of c is equal to 7. This is an intermediate value theorem problem. All right, so here is the argument we're going to make. What is g of -4? Well, that's 0. So g of -4 equals 0. And g of 5 is 8. G of 5 equals 8. Since 0 is less than 7 is less than 8. So since 7 is between 0 and 8, and since g is a continuous function, there has to be a value x equals c for which g of c is equal to 7. So that's what we're going to write. So since 0 is less than 7 is less than 8, and since f is continuous on the closed interval from -4 to 5, by the intermediate value theorem, there must be a value x equals c on the open interval -4, 5, where g of c is equal to 7. Explain why there must be a value x equals d on the open interval -4, 5, such that g prime of d is equal to 8/9. So this is going to be a mean value theorem problem. So let's write the average rate of change. Here we have g prime of d equals, and we're going to put g of 5 minus g of -4 divided by 5 minus -4. And so that's going to be equal to g of 5 is 8 minus g of -4 is 0 over 5 minus a negative 4 is 5 plus 4, and that's equal to 8/9. So here's what we're going to say. Since f is continuous on the closed interval from -4 to 5 and differentiable on the open interval by the mean value theorem, there is a value such that g prime of d equals 8/9. Part C asks, does g of x have a local maximum, local minimum, or neither at x equals 3? Justify. Alright, let's go back and let's take a look at our graph. I'm sorry, not graph, our table. So at x equals 3, we know that g prime of 3 is equal to 0. So that means that 3 is a critical value for f. So let's write g prime of 3 equals 0, and that is a critical value for f. And g double prime of 3 is -2. G double prime of 3 equals -2. So that means that g of x is concave down at x equals 3, and g of 3 is a local... Alright, so since g prime of 3 is equal to 0, it's a critical value. That means it is going to be an extremum. It's either going to be a maximum or a minimum. If the graph is concave down at x equals 3, it's got to be a local maximum. And I mean, you could just draw a picture, right? And it's like, okay, it's got to be, it's on top of the hill. So and so that local maximum value is going to be the y value, which is 4 at x equals 3. And that's by the second derivative test. So all of the information we needed was in that table, and table problems are very popular on the AP exam. In part D, they ask, can concavity of g of x be determined on the interval 4 less than x less than 5, why or why not? So this is an open interval, and it's the interval that we're given in the table. Let's look back, and I think they actually mean -4. So let's make that correction. -4 less than x less than 5. So on the interval from -4 to 5, I have the endpoints, but I only have one point in the middle, and there's infinitely many points missing that could be potential points of inflection. So there's not enough information. So let's make an argument for that. So no, there is not enough information to determine concavity on the open interval -4, 5. We only have endpoints and x equals 3. So there are infinitely many points missing to establish concavity. So if they'd given us a graph, we could have made an argument. But because they gave us a table, that's discrete information, and it doesn't deal with a continuous function in such a way that we can talk about concavity of that function. So our test for concavity is if f of x is greater than 0 on a particular interval or for a particular value, then on that interval or at that value, f is concave up. If f double prime is less than 0 or negative, then the graph of f is concave down. And they've given us a table here that summarizes the relationships between f prime and f double prime and gives us the description for the function f. So if f double prime is positive and f prime is positive, f is increasing and concave up. If f double prime is positive and f prime is negative, f is decreasing and concave down. If f double prime is positive, f prime equals 0, we have a relative minimum and it's concave up. F double prime negative. If f prime is positive, it's increasing and concave down. F prime is negative, it's decreasing and concave down. F prime equals 0, we have a relative maximum, and it's concave down. And if f double prime equals 0, it's increasing at an inflection point. If f prime is negative, it's decreasing at an inflection point. And if both f prime equals 0 and f double prime equals 0, the function is smooth, level, and a possible inflection point. We'll see you next time.